is I would like to present our project economics for our project. This is the step for our economics, which is the first one. We calculate the purchase cost of equipment, total capital investment, total production cost, revenue and payback period. This is our purchase cost. We have 3 storage tank, 2 reactors, and some of heat exchangers, 2 pump, 2 compressor, and vessels. All of them, the total of them, about 8,500,000. This is our total capital investment. From our total this is the calculation from our purchase cost of equipment. We calculate, and then we plus all the factor and we multiply with the purchase cost equipment, and then we get PPC, which is 26 million, about approximately 27 million, and then we multiply the PPC, and then we get the fixed capital investment, which is about 37 million. And then we calculate the TCI. We plus fixed capital investment with working capital, where the working capital is 11% of the FCI, and the total we get TCI, which is 41 million, about 41 million. And then we got the total production cost. The variable cost is raw material and utilities, and then we have fixed costs. We sum all, and then we can get around 41 million, with annual operating, which is 55 million. This is our revenue, the price of reformat, the production capacity, and the revenue generated is the product of product market price multiplied with plant production capacity. This is to calculate our payback period, which is our depreciation is about 2 million, and then this is our startup investment. Year 1 we have about 8 million, year 2 8,000 million, and year 3 is 2.5 million. And then our payback period will be starting at year 7. Stop. This is my major reactor. For my part, I do desulfurization reactor, which is the code is A1000. This is my design methodology. The first one, I determine the type of reactor, the design and operating parameters, and then reactor sizings. Then I go for material selection, closures and flange, technical drawing, and the last, after all the design is complete, I create the operating procedure. This is my basis selection for the reactor. I select multi-tabular fixed bed reactor. The reason is because the catalyst and the reacting species are from different phases, which is heterogeneous, and the catalyst is cobalt molybdenum, because cobalt promoter have higher affinity to attract sulfur atom in receptance, and the size is 2 mm. Is to maximize the contact surface with naphtha gas. The construction material is stainless steel 321, because it means the design pressure and temperature, which is 4.2 megapascal and 315 degrees Celsius. The type of closure is toric spherical head. because it has less concentration as compared to flat plate. The gasket material is soft material, and because it meets the maximum design of seating stress. The tube material is stainless steel 502 because it resists to corruption. And last, insulation material, it's from mineral wool. The reason I choose mineral wool because it will not burn until the temperature beyond 1000 degrees Celsius. This is my sample of calculation. This is how I get the bundle diameter. And then for the reactor diameter, I calculate the diameter plus 2 times of the thickness. And then for the reactor height, which is the height of the shell, which I times height of closure with height of tube. The wall of thickness of the shell, I calculate the P design times with diameter divide with 2 Fj minus P and plus with C. And this is for the nozzle sizings, which is the diameter. This is how I calculate it. This is my specification sheet, which is if it have the diameter of inlet is 6.3 and the 6.3342 meter. Diameter of outer is 6.3842. This is my design code. The maximum working pressure is 82,000 kilopascal. About the design pressure is 4,200. This is my specification. This is my specification sheet. I have only one reactor. The orientation is vertical. The type is fixed bed reactor. It is insulated. The content of my reactor is untreated naphtha with diameter inner 6.3342. Diameter outlet is 6.3842. My diameter height is 4.19. My maximum working pressure is 82,000 kilopascal with the design pressure for 4,200. The pressure drop is about 330 kilopascal, and the operating temperature is 300 and design temperature is about 315. The inlet flow rate is about 5,048 meter cube per hour with the outlet 5,158. The number of pass is only one. So this is for the shell thickness is 0.02 with corrosion allowance about 0.002 meter. The starboard type is skirt and the end type is story spherical. The thickness of end type is 6.13 millimeter. My gasket width is 8 millimeter with 2 nozzle. The thickness of insulation is 100 millimeter, and my number of tubes is about 1,800. The reactor weight is 926 tons. So this is my catalyst, which is cobalt molybdenum with the density of 0.68 gram per milliliter with the weight of 842 kilogram. And this is my technical drawing, which is the height. This is the tube and the nozzle with the height of the tube, which is 1.911 meter with the height of the shell. This is the nozzle inlet and outlet. Okay, thank you.
Assalamualaikum warahmatullahi wabarakatuh. So, my name is Nurul Aina Billah. I will be presenting about waste management. So, um, this is the type of waste that contained in our plant, which is first we divided into three, which is we have solid, liquid, and gas. So, for solid waste, we have spent catalyst, which is the catalyst that we had used. So, we have to dispose it properly. And then we have used packing, which is the packing is used in the amine absorber and the liquid extraction unit. And then we have plastic, rags and papers, and used gloves as our solid waste. And then for liquid waste, we have oil and water mixture, which is come from the hydrocarbon itself, and the solvents if there are in any case of spill or any emergency. And then we have also chemicals from lab. And then we have for gas we have H2S gas and hydrogen. So for environment under waste we have to comply into three types of law, which is state in Environmental Quality Act 1974, which consists of Environmental Quality Scheduled Waste Regulations 2005, Environmental Quality Sewage and Industrial Effluents Regulations 2009, and Environmental Quality Clean Air Regulations 2014. So basically, for scheduled waste is basically we focus on the solid waste that we have in our plant, and then for industrial effluent refers to our wastewater treatment, which will treat our liquid waste. And then for environmental quality, for clean air regulations is basically we refers to any emissions that we are released from our plant. So for solid waste management, most of the solid that we had in our plant are basically listed in scheduled waste code, and then we have follow and comply to the scheduled waste regulations 2005. And before we dispose to the prescribed premise, we have to separate the waste according to their code, and then we will send it to the prescribed premise for further treatment and disposal. So for solid waste management, these are the uh, list of the waste that we have. We divided into schedule, which is four schedule, which is first we have metal and metal bearing waste. Second code we have waste that containing principally organic constituents, which may contain metals and organic organic materials. And then for code 3 we have waste that contain organic constituent, which may contain metals and organic materials. And then for fourth scheduled, we have waste that contain either inorganic or inorganic constituents. So according to the scheduled waste regulations, all these kind of waste have to be segregated into based on their code before it is disposed. And then we have to put it in a suitable container, which is we have a wooden crate, we have bunk hole, and we have any jumbo bag. So all these waste will be kept in this kind of container, and every waste must have be labeled on the container before it is disposed to the prescribed premise. Moving on, we have liquid waste management. So liquid waste management, we are referring to our industrial effluent treatment system, which is we have three types of treatment. First, we have preliminary treatment, we have primary treatment, and tertiary treatment. In preliminary treatment, basically we have bar screen, grid chamber, and equalization tank, which is the purpose of having preliminary treatment is we want to remove any coarse or debris solid in order to protect pumps, valve, and downstream pipelines. And we want to ensure all treatment process are reliable and effective, because we don't want any damage in the system. And then this kind of solid have to be removed before because it will tend to damage the pumps or any operational damage in the system. And then we want to improve the performance of the downstream process. Moving on to the primary treatment, we have primary sedimentation tank, anaerobic tank, primary sedimentation tank. Because we want to let the heavy and bigger solid to sediment at the bottom of the tank. So this type of this level of treatment is basically we are collecting the sludge, solid sludge, from the wastewater before it will be sent to the next treatment, which is secondary treatment, which is we have anaerobic tank and a secondary clarifier. So for your information, we are actually using biological treatment, which is we are using microbes, which the microbes will be eat all the waste in the wastewater, and then it will become bigger and bigger, and after some times it will be sent to the secondary clarifier, and it will be settled at the bottom of the clarifier, and the sludge that we get is we will be disposed to the sludge bed, or some of it will be sent back to the anaerobic tank to maintain the concentration of microorganisms in the anaerobic tank. For tertiary treatment, the purpose is to remove any bacteria or virus from the treated water. So we call it as disinfection tank, which is we are removing water. We are putting some chemicals to kill the bacteria and any virus, such as for example, we can use chlorine or any fluorine to kill the bacteria. And then we have sludge dewatering. The sludge that we collect from the secondary treatment will be sent to the sludge dewatering system to remove water in it, and before it will be placed on the sludge bed to be sold to other parties. And that's all from me. And then I will be moving on to the major equipment, which is I am doing furnace. So basically furnace is one of the heat exchanger where it is used to heat up the feed before it will be sent to our main reactor, which is catalytic reforming reactor. So this is the details and operating condition of our furnace, which is we have 96% efficiency with this kind of required heat duty, and we are using methane because at first we want to use benzene as our fuel. However, the fuel that we get from our plant is not sufficient to be supplied as a fuel in the furnace, because we only produce about 5,000 benzene per year, while we need more than that to use as a fuel in the furnace. Hence we have to use other fuel, which is methane, which is a bit cheaper than benzene, as a fuel for our furnace. So this is the mechanical drawing of my furnace. So if you can see here, this is the radiant section, convection section, and this is the stack of our furnace. So this is the tube for the furnace, and then this is the reaction and parts of the furnace. The efficiency after we calculate, we get 96% of efficiency. And then the temperature of stack, after we calculate using the graph, we got 842 Fahrenheit, and using the chart to get the gas temperature of the gas, which is 842 Fahrenheit. And then we have to calculate the total amount of Q from the Q furnace, Q air, Q minus Q oil, and Q exhaust. And then we got this value as our amount of heat flow rate, which is 1, 2, 3, 4, 5, 4 billion, 4.2 billion of BTU per hour. And then this is the area of our tube that we calculate. And after we calculate, we divide it with the amount of Q. We got 11 tubes for our furnace. That is for the. And then we go for the radian section. This is the dimension of our radian section. This is we got from our paper, the ratio that we have to use. And then this is for the convective section. We, after calculating with the number of tube, we got 16 tubes for convective section, and each tube consists of 4 passes. So this 16 tube we have to divide it with number of passes, which is 4. So we got 4 rows of passes. And then this is the length of our convective section, width and the height. Moving on, we have to calculate the stack section, the dimension of the stack. So this is the formula to calculate area, which is area equals to heat flow rate divided into the volume. So we are assuming that the stack gas should not exceed by 10 meter per second. So we are assuming the velocity of the gas is 10 meter per second. Hence we have to divide it with the total number of heat required with the velocity, and then we get the area, and hence we get the diameter of the stack, which is 0.363 meter. So this is the material of our furnace. This is for casing, and this is for our insulation materials. For casing, we are using carbon steel, and material of the insulation, we are using ceramic fiber. So this is the mechanical sheets of our furnace. So that's all from me. Thank you.
Assalamualaikum, my name is Tengku Nurul Syafiqah, and now I will explain about my major equipment, which is ambient absorber or A1001. So this ambient absorber is used to separate H2S from our gas stream, because we do not want any H2S in our gas stream. Okay, before I further explain regarding my ambient absorber, I will first explain about how I design my absorber. Okay, first I set up the product specification. After that, I determine the operating condition and the number of transfer unit. Then I do the sizing of internal column, such as the diameter of the column. Next, I proceed to the mechanical design. After I done the mechanical design, I then do the technical drawing. And last but not least, I list out all the setup and shutdown procedure for the ambient absorber. So this is how our ambient absorber will work. First, the gas stream will enter at the bottom of the column with mass flow rate of 3,108.89 kg per hour. At the same time, our solvent, which is diethanol amine, will enter at the top of the column with mass flow rate of 7,192.63 kg per hour. So this amine and gas will contact into each other, and then the amine will absorb H2S from the gas, which resulting in our desired product that flow out at the top of the column, which is sweet gas. So this sweet gas is the gas that are free of H2S, or in other words, there is no H2S in this sweet gas. So the amine that absorb H2S earlier will flow out at the bottom of the column, which is rich solvent. So as mentioned earlier, this rich solvent is contained of amine and also H2S. So this rich solvent will be sent to ambient recovery unit. So after the ambient recovery unit, they will be recycled back to the top fat of the column as solvent. Now I will explain about the selection of the column. So I decided to use packing column for my ambient absorber design. Why? Because first it has continuous contact, or in other words, it is easy to operate as the liquid or the solvent can continuously absorb the gas, which makes the separation or the absorption more efficient. Other than that, it also has no pressure drop, and the liquid also flows at a steep film over the packing. Moreover, it also has lower propagation and material cost. Other than that, packing column have so many materials that we can choose to construct our packing column. So in other words, we have more choice to choose for the materials to construct the column. Last but not least, the foaming liquid can be handled more readily in packing column compared to others. Okay, so for the type of packing, I decided to use interlock siders. Why? First, because interlock siders have large contact area. Other than that, it also have open structure and high bed porosity. Moreover, interlock cider also have high chemical resistance. And last but not least, it is also have lower cost compared to other material due to its simpler form. So that's why I decided to choose packing column and interlock cider. Or in other words, I decided to choose interlock cider packing column for our ambient absorber design. Let's proceed to the calculation. For calculation part, I will just explain about the important things only, which is the diameter of the column, height of the column, and the operating velocity and floating velocity. Okay, for the diameter of the column, first we need to calculate the gas loading first. Or we know this as G star. G star here means the gas loading. So we calculate the gas loading by using this equation. K4 and Fp is the constant that we get from the graph and the table from the textbook, depending on the materials that we use. So by using the formula, we get the gas loading, and from the gas loading we can calculate the area by dividing the gas flow rate by gas loading, or in other words, we divide the gas flow rate by the gas loading, and we get the area, which is 0.46 meters squared. So from the area, we can get the diameter, which I take the meter, I get 0.76 meter. This is the internal diameter. Next, we proceed to the height of the column. So for the height of the column, we can calculate it by multiply the number of transfer unit by the height of transfer unit. So by using this formula, I got the height of column equals to 10.76 meter. So after that, we calculate the operating velocity. We use this formula equals to 0.046, and we substitute all the formula and find the G. Our G, which is operating velocity, is equals to 4.35 meter per second. Last but not least, we calculate the floating velocity. For the floating velocity, we use the same formula as above, but equals to 0.13, and we substitute all the value, and we got G. I got G equals to 7.31 meter per second. And after the calculation, I discovered that operating velocity is 59.48% of the floating velocity, which is it is in the range. It is in the good range. So this is my mechanical drawing. So the gas stream will be fed to the bottom of the column, which is here, with the size of the nozzle 107 millimeter. At the same time, the dry ethanol amine as our solvent will enter at the top of the column here with 63 millimeter in the liter. So our resulting desired product, which is sweet gas, will flow out at the top of the column, and the amine, which solvent, will flow out at the bottom of the column. So this here I labeled all the assemble the gasket and the bolt later. So for detail, you can refer to my video report here. In that, I show the calculation in detail. So last but not least, here is my specification data sheet. Okay, here you can see my internal diameter is 0.7 cm. My column height is 10.7 cm. Number of tray is 32 and number of stage is 15. So the operating temperature is 40 and the operating pressure is 6,800 kPa. So here I have list all the value, all the nozzle, inlet and outlet value, the internal and the inlet, the inside and outside column diameter, the thickness, and also the nozzle diameter, the bore diameter, dead weight. And also here I also list down the materials that I use, which is for vessel I start to use carbon steel. For the skirt also I also use carbon steel. For packing I start to use interlock-sided. Why I use carbon steel? So because it is stronger, less expensive. It also have high resistance to corrosion compared to other material. So that's all from me. Thank you.
Yeah, start on your account lah.
1, 2, 3. For my major equipment, I'm designing the catalytic reformer for the reforming of hexane. First, to give an introduction towards the process, the inlet of the feed is coming at 450 degrees and at 1030 kPa, and the mass flow rate is about 11,000 kg per hour. So the feed is mainly composed of hexane and some more of and lactate. In the catalytic reformer, we only consider the dehydrocyclization reaction as our main reaction, which produces MCP and hydrogen. There's another side reaction which produces from the hexane, it produces benzene and also some amount of hydrogen. Okay. Moving forward, we designed the catalytic reformer, the reaction kinetics based on the catalyst. Okay, first we look at the absorption of hexane on the catalyst surface, which is given as A as hexane and being absorbed into the catalyst as the first reaction. And then this, after derivation, this overall reaction rate for absorption. Next, we look at the surface reaction at which the hexane turns into MCP and also hydrogen. Okay, this is the reaction. Hexane turns to MCP and hydrogen. And after derivation, this is the given rate law for the surface reaction. Next is the desorption. The desorption of the MCP and also hydrogen from the catalyst side. Okay, this is given by the two of the equation, and this is the two rate laws. Okay, from the literature, we find that the rate determining step or the slowest step among these three main reactions is the surface reaction. So based on that, we take the surface reaction as our overall reaction for this overall rate of reaction for this process. Okay. So based on that, we further derive it based on the other constants. So because of this, we are considering this, we can consider that the reaction of the absorption and desorption reaches equilibrium earlier than the surface reaction. Hence, the rate is 0, and we can further simplify the other two equations, and we can get this equation as our overall rate law. Okay, so from the literature we can get all the constants, and we are left to find out only the partial pressure, as all the constants are given here. So the partial pressure is further calculated using the equation from correction drilling, and which is based on inlet concentration, temperature, conversion, and also the ratio between the outer pressure and inner pressure. Okay, and after calculation we get the partial pressure at the outlet at 5 hexanes, 80 kPa, MCP 450 kPa, and same for hydrogen. Okay, so based on all of this value, the previous value, we can plug in back into the rate law and we get the rate of fraction. Okay, so based on that, we know the inlet flow rate, and we know the rate of fraction, and we calculate the rate of the catalyst. Okay, so from the calculation we have gotten about 44,000 kg of catalysts being used for this reaction. Okay, from our literature you can find that the catalyst best to suit for this reaction is a trimetalic modified aluminum oxide. Okay, so and the catalyst size used is 3.18 millimeter. The bait void is 0.35. Bulk density is 850 kilogram per meter cube, and the space velocity and superficial velocity is reported as in literature from the experimental data. So using this data, first we calculate the molar density at standard temperature and pressure, which gives us a value of 0.04 kilomole per meter cube, and using that value we are dividing the molar flow rate with the molar density at standard condition, can get the volumetric flow rate at standard condition. Okay, using the volumetric flow rate at standard condition, dividing it with the space velocity, we can get the volume of the bit of the reactor. Okay, and then using the volumetric flow rate getting from the simulation, the actual volumetric flow rate, dividing it with the superficial velocity, we can get the area of the bit. So we now know the volume and the area. We are left to find out the diameter. So based on the area, we plug into the formula to get the area. We can get the diameter, which is about 2.94. So now we have to downsize it to allow some amount for the thickness of the vessel and also some corrosion allowance. So we have reduced the diameter to 2.5 to allocate some space for thickness and corrosion allowance. Next, using this thickness, we again calculate the area of the cross-sectional area, and we calculate using that area divided by the mass, divided by the earlier calculated volume or the bit, we can know the bit length or the reactor length, and then we add an allowance of 1 meter up and down for to put the dish for some movement of air, movement of gas inside the reactor. Okay, next, for mechanical design, the design temperature is allowed at 5% more than the operating temperature and pressure. This is the calculated values, and the shell thickness are calculated using this formula, and we got about 14 millimeter millimeter, and thickness of the minimum thickness is calculated as 26 millimeter. Next, this is the mechanical design. As you can see, because the reactor traction is happening at an endothermic condition, we are using a steam jacket around the reactor for continuous heating. And this is the bit, catalyst bit, and the length is about 16 meter, and thickness of the thickness of the wall is about 14 millimeter. So that is the equipment design for the catalytic reformer. Thank you very much.